Okay, now these two are very, it looks like very simple, very trivial. Okay, but let me show you some of the interesting examples that we have. Okay, the first one is, okay, let's look at this number, 1997. Okay, so this is a number that has some special meaning for people who are from Hong Kong. Okay, so this is a special year for us. Okay, 1997. And now we are showing that, okay, so let us look at all the numbers of this form. So there are a lot of numbers, but let us look at all the numbers of the form that, okay, let us look at all the numbers that has only 0 and 1 inside as the digits. Okay, and in particular, let us look at the numbers that begins with 1 and then ends with 0. So this is a possible number. This is what? This is 111,000. Okay, this is a number of this one. Okay, you can have a number of, this is 100. So this is of the form, you start with 1 and then you end with a bunch of zeros. Is that okay? Now, we want to show that among all these numbers that begins with 1, so there are a couple of 1s, and then it ends with a couple of zeros, one of them, or at least some of them, is a, so we want to show that there exists some number of this form that is a multiple of this special number, 1997. Okay. Wow, you may think that it is not, how is that possible? So 1997, how does it goes to 1111, something like this? Okay. Okay, but then we can show that it is okay. Do you understand the question? So there is a number of this form. It begins with a lot of 1s, and then it ends with a lot of zeros, but then overall this number is divisible by 1997. Okay? So it's strange, but it's true. Okay? Okay? Let's do this. Okay? Let's look at the numbers. Okay, in particular, let's look at the numbers. The first one is 1. Okay? The next one is, this one is what? This one is 11. This one is what? 111. Is that okay? And then 1,111. And then this is 11,111. Is that okay? Is that okay? So we look at a lot of these numbers. Let us look at how many of them. Let us look at 1998 of them. Is that okay? So the last one will be what? We have 11111, but then there are 1998 ones here. Is that okay? So why am I looking at these numbers? So for each of these numbers, I'm going to divide this by 1997 and get the remainder. So I'm going to take the modulo of this number when it is divided by 1997. Is that okay? Is that okay? So it is, let's say this number is x, then I'm going to compute x modulo 1997 here. So this is 1, this is 11, this is 111, this is 1111, and then this one, I don't know, this one is okay, going to be what? Going to be how many? 3, 3, 3, 3 is 12, so it is going to be 1, 2, 3? No, 1, 1, 2, 3. Is it? Anyone has a calculator? So 1997 is like 2,000. Is it okay? So it's 15. 26. So if I get 10000, and if I divide this by 1997, I will have a remainder of 15. And then this part I still haven't taken care of, so it becomes 1126. Is that okay? Something like this. So everyone has a remainder if you divide this by 1997. Okay? But then what? What are the possible remainders when you are dividing a number by 1997? What are the possible remainders? How many of them? if you divide the number by 1997, so you can have a remainder of 0 if it is a multiple of 1997, right? You can have a remainder of 1, 2, and so on, right? How many of them at most? So how many different cases are there? Very good, 1997, okay. Now, remember, I'm taking this magic number 1998. So there are 1998 numbers, and then each of them, we are going to divide this one 1997. Each of them, you get a remainder. So 2 of them must have the same remainder. We can find 2 of them with the same remainder because there are 1998 possible there are 1998 remainders, and then each one of them need to choose one of these 1997 remainders. Okay, so 2 of them has to have the same remainder. Does that make sense? Okay, think about this. If you pick any 4 numbers, you divide them by 3 and take the remainder, then 2 of them has the same remainder. Does that make sense? You pick any 4 numbers, let's say 17, 25, 48, and then 2. Okay, 17, 25, 48, and then 2. And then we get the remainder. So 17, if you divide it by 3, then the remainder will be 2. Is that okay? 25, if you divide it by 3, the remainder will be 1. 48, if you divide it by 3, the remainder will be 0. Is that okay? 2, when you divide it by 3, the remainder will be 2. So you get 2 numbers or more with the same remainder. Is that okay? This is pigeonhole principle. There are only 3 options, but then there are many things that needs to pick these 3 options. In that sense, 2 of them or more of them will be mapped to the same hole. Is that okay? So in these 1998 numbers, each one has a remainder, and then what? And then 2 of them, or at least 2 of them, will have the same remainder. Is that okay? Okay, good. Now, let's use this part. So we know 2 of them have the same remainder. I don't know which one, but they are of the same form, like 1, 1, 1, 1, 1, 1, 1. And then the other one is maybe 1, 1, 1, 1, 1, 1, 1, 1. Is that okay? Let's say these are the 2 numbers with the same remainder. Okay, so this one is equal to 1997 times some integer k plus a remainder r. And then let's say this one is 1997 plus another number k prime, but then they have the same remainder. Is that okay? Now, these 2, they have the same remainder, so the difference, if you the difference, what is the difference? So we write down the difference here. The difference will be equal to 1997 multiplied with k minus k prime. Is that okay? So the difference of these 2 will be what? Will be a multiple of 1997. Is that okay? Good. So how does the difference look like? So this is a bunch of 1s, and then you are minusing another bunch of 1s. So how does the remainder look like? How does the difference look like? It must be a bunch of 1 followed by a bunch of 0s. Is that okay? Okay. And in that sense, we have just created a number. We have just proven a number which is a multiple of 1997, and then it is of a special form. It starts with 1 and ends with 0s. Okay? Okay, amazing, right? I think this is quite amazing. Yeah, if you are okay with this, could you please raise your hand? Okay, good. Now, so we can do it a little bit more. This number, if I have a number of this form, which is a multiple of 1997, actually, the 0s are not important. Reason, okay. So if I have a number like this with a bunch of 0, I can write it down as it is a bunch of 1s multiplied with 10 to the power something. Okay. And actually, if I write down as 10 to the power something, I'm actually saying that I can write it down as 2 to the power something times 5 to the power something. Is that okay? Is that okay? Now I'm claiming that there is a number of this form which is a multiple of 1997. So it is equal to 1997 times some number, let's say m. Okay? If you believe that, okay, if you believe our teacher in the secondary school or the primary school that each integer, this is an integer, right, has a unique prime factorization, then in that sense, it can factorize the numbers here uniquely into primes, then the 2 must come from this m rather than this 1997. Because 1997 does not contain any 2 inside. So you can remove all the 2's by dividing it here. And it is still an integer. Is that okay? And all the 5's, the factor of 5 does not come from this 1997 because 1997 is not divisible by 5. So you can also cross out this 5 by putting this 5 here. And then this part is still an integer. Is that okay? Or alternatively, 1997 cannot divide 2, it cannot divide 5. There's nothing related between 1997 and 2 and 5. So 1997 must itself divide this number. Is that okay? So this is an extra story. So once we have known a certain number of the form 111 and then 000 is divisible by 1997, then we can strengthen our argument by saying that, okay, we don't need the zeros. All the zeros, you can cross it out. The remaining part, which consists of all ones, is still divisible by 1997. Okay? Okay, good. If you don't understand this, don't worry. You can find me, okay? And we can discuss it after the class. Okay, and then another example. Okay, let's look at this equilateral triangle. So this is a triangle that has all sides equal. Each side has length 2. And then we are going to put 5 dots inside. So put 5 points inside. So we are going to put 5 points inside this triangle. We want to show that no matter how we put these 5 points, then we can find 2 points such that the distance is the distance of some of the points that you have chosen is less than or equal to 1. Is that okay? So no matter how you put the points, maybe I'm putting a point here, a point here, so just inside this triangle, maybe a point here, and then maybe a point here, something like this. Then, so we have a lot of distance. Then we can show that at least one of the distance between the 2 points has to be less than or equal to 1. Maybe this one is less than or equal to 1. Okay, how can we show this? This is really a tricky problem. Okay, so I chose this example here because it can be proven easily by Pigeonhole Principle. And then to prove it by Pigeonhole Principle, we have to think about what are the pigeons and what are the holes. How many pigeons and how many holes? So here in this example, let's guess how many pigeons we are going to create. How many? How many pigeons? We are going to put 5 points inside, right? So this is the thing that we are going to choose randomly. So it is like the pigeons, because the pigeons flies back randomly and choose a hole, right? So there are 5 pigeons. So 5 pigeons. Let's use your creativity. So let's say there are 5 pigeons, and then we are going to use Pigeonhole Principle. So perhaps we should be choosing 4 holes, right? But then we want to have a property that if 2 pigeons are in the same hole, if two pigeons fly back to the same hole, then this will imply the distance is less than or equal to 1. So is there a way to have this kind of guarantee? So first of all, we need to create 4 holes, and then if somehow 2 points are inside the same hole, then the distance will be less than or equal to 1. So how should we create the holes? Anyone have seen this problem before? No? Okay, anyone has some idea? Okay. There is a triangle. We want to create 4 holes based on this triangle, such that it has a property. If 2 points are inside the same part, they will have distance less than or equal to 1. This is a 2 by 2 by 2 triangle. Okay. I guess some of you may have got the answer, but let me tell you. So let's do this. So you choose the midpoint here, the midpoint here, the midpoint here. Is that okay? So join this thing. Each one of them is a 1 by 1 by 1 triangle. Is that okay? You have 5 points. You have 5 points. Then that means that one of these triangles, all the triangles are identical. One of the triangle must have at least 2 points inside. Is that okay? And then for any 2 points inside the same triangle, they must have distance at most 1. How do we know? Okay, yeah, you can see, okay, by geometry it is at most 1. Or if not, let's join the 2 lines, put it here, okay. There are 2 angles here, one must be larger than 90 degrees, the other must be smaller than or equal to 90 degrees, and then you shift to the side that is with 90 degrees, so you have a line here, and this line is longer than this line, and this line is longer than this line. Is that okay? And similarly, you can move this here so that this line is longer than this line. Okay, this line is longer than this line is longer than this line. Is it okay? So in that sense, if you pick any 2 points inside a triangle, the distance must be shorter than the distance between an edge. And the edge has length 1. So in that case, the distance is smaller than or equal to 1. Okay? So it proves, this is very powerful. It proves all the possible cases. You don't know how the 5 points are distributed. There are infinite configurations. There are infinite ways that you can draw 5 points. But no matter how you draw it, then there must be 2 points with distance less than or equal to 1. And then you can prove these infinite many cases by using a simple drawing. You draw it like this. Pigeonhole principle tells you that this is going to be correct. Okay? Okay? Okay, one more. Let me give you one more example. And then there are more examples to come in the next class. So you have, so you are having, let's get some 6 vertices. So these are some vertices. And then you can join. So we are going to join every pair of vertices by a line in one of the 2 colors. Either it is an orange color like this, or it can be white like this. Is that okay? But you need to join every one of them. So maybe I have a white here, and then a white here, and then maybe I have a orange here, and then whatever, orange here, and then orange here. Did I join everyone? This one. Let's say I have an orange here. Okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So I have joined it. Okay. So we want to claim that inside this, no matter how you color these edges, you must be able to find either a white triangle or an orange triangle. So there must be some white triangle or some orange triangle inside. So do you find the white triangle? Okay. I do not mean that there must be one white triangle together with one orange triangle. I do not mean this. What I mean is that, okay, you either find a white or an orange or both. Okay. Okay. But in any case, if you cannot find a white, there must be an orange. If you can't find an orange, there must be a white. Okay, so in this case, do we find a white triangle? Yeah. If you pick this vertex, if you pick this vertex, and if you pick this vertex, then it is a white triangle. You understand my point? Okay, and in this particular example that we draw, there are also an orange triangle. We can have this one, and this one. This is orange triangle. Okay, but then 6 is a magic number. Okay, so let's say if I repeat this argument for 5. So inside the 5, if I color it using only 2 colors, is it always possible to find a white triangle or an orange triangle? Now I'm going to show that it is not the case. Okay, it is not always possible. If I do something like this, the whites are here. Is that okay? The orange are here. So it is beautiful. It's a star contained inside a pentagon. Okay, then you can see that you don't have any orange triangle. You don't. Yeah, there is no orange triangle inside. You don't. So by means of a triangle, I mean it has to have vertices ending at least five of them. Okay. So if I pick these 3, then 2 orange, 1 white. If I pick these 3, 2 orange, 1 white. If I pick these 3, 2 white, 1 orange. There is no orange triangle. There is no white triangle. Okay. But what I'm showing here is that 5, there is no guarantee. But for 6, it is always guaranteed. Okay? Okay? So why? Why is it the case? Okay? So let me prove it here. Why is 6 the case? It is going to apply Pigeonhole Principle once. Okay? So let's pick a particular vertex. Okay? Let's pick a particular vertex. So for this vertex, in the case of 6, it has to make 5 edges to the other vertices, right? Okay? It has to make 5 edges. I don't know it is going to make what kind of edges to these 5 vertices, but I know that for a certain color, it must appear 3 times or more. So if they are all white, then white appears 3 times or more. If 2 of them are white, 3 of them are orange, then orange appears 3 times or more. Is that okay? Now there are only 5 edges, and there are 5 edges, but there are only 2 colors. 5 divided by 2, if you take the ceiling, it is equal to 3. So using the generalized principle, one kind of color appears 3 times or more. So maybe this one, and this one, they are using the same kind of color. I'm using green here because I don't know whether it is white or it is orange. But I know that a certain kind has appeared 3 times or more. Is that okay? Is that okay? So let's take a look of these endpoints. If these 2 are joined by the same color as green, then we have a green triangle. Okay? So if these 2 are joined by green, then we have a green triangle. So for the case that we don't have a green triangle now, let's say they are joined by the other color. Okay? Now we can repeat the same argument. If these 2 are joined by green, the same color as this one, then we have a green triangle. So in that case, if we either have a green triangle now, or if we do not have a green triangle, then this must be joined by another color. Is that okay? Okay? Now finally, we will repeat this argument again. Look at these 2 vertices. If they are joined by the green, then we have a green triangle now. But if they are not joined by green, then they have to join by the other 2 colors, like this. Is that okay? Okay. So if we do not have a green triangle, then these 2 are joined by the other color, these 2 are joined by the other color, these 2 are joined by the other color. So we have a triangle of the other color. Is that okay? Okay. So usually, okay, this problem is usually described in another way. It is like there are 6 people, they are inside the lift. Okay. Let's say every pair of people, they are either friends, so they know each other, or they are not friends, so they do not know each other. Is that okay? So in this case, we want to show that inside the lift, inside the lift with these 6 people, either we can find 3 of them, they are mutual friends, so they are friends to each other, or we can find 3 mutual non-friends, so they are not friends of each other. So this is the same problem as this one. If they are friends, we are using one kind of color, let's say white. If they are not friends, we are using a different kind of color, let's say orange. So we are saying that if you join all the edges by white or orange, then you can either find a triangle of white or a triangle of orange. Is that okay? Okay. So this is an interesting result. If I have time, I will talk about it more. Okay. Okay. So let's end the class today, and next week we will talk about more difficult examples.